Okay, in this lecture, we're going to do the following problem. This is going to be an isosceles right triangular plate that is being submerged into a swimming pool 2 feet below the surface of the swimming pool. We want to find the force exerted by the water against one side of the plate. Alright, so let's get started. We have the plate right here. The XY axis. We're gonna go ahead and put the plate right here, so it will be something like this, maybe a little bit more like that. It's supposed to be a right rectangular plate, and we're gonna set it so that the vertex right here is at the point 0, 0 on the x-axis, and then this is gonna be the y-axis. I'm gonna go ahead, and because the plate is 3 feet long, this point right here will be the point 3, 3, and I'm just gonna go ahead and put this right here is the line y equals to 3, because the plate is submerged 2 feet below the surface of the swimming pool. We're gonna have the surface of the swimming pool at y equals to 5. Alright, so in order to find the force exerted by the water on against one side of this vertical plate, we're going to draw a horizontal strip y units from the bottom of the plate right here. And so then if this is y, then the depth of the plate will be, or that strip will be 5 minus y. Okay, this strip will be at the point xy, but since this is a right triangular isosceles and it satisfies the equation y equals to x, then this point really you can write it as y. So therefore the length of this horizontal strip will be y plus y, which will be 2y. So this is L of y. This is supposed to be fresh water, and the weight density of fresh water is equal to 62.4 pounds per cubic feet. And since the isosceles is 3 feet high, the force exerted on one side of the plate by the water is the integral from a to b, where a in this case are the y values from 0 to 3, of the density of the water times the depth of the strip. And with respect to 1. So with this, we have the integral from 0 to 3. Oops, I forgot Ly dy, which is the length of the strip. So we have 62.4 for the density weight of the water, and then we have the strip depth is y minus 5, actually 5 minus y, so 5 minus y, and because the length of the strip is 2y, this is the force exerted by the water on one side of the plate. We can take the 62.4 times 2 outside of the integral, and we'll have something like 124.8 times the integral from 0 to 3, 5 minus y times y dy, or you can write it as 124.8 times the integral from 0 to 3 multiplied by y, so we're going to have 5y minus y squared with respect to y, and this is 124.8 times the integral of 5y squared divided by 2 minus y cubed divided by 3 as y goes from 0 to 3. Plug in the 3 for the y and simplifying everything out, we get 1,684.8 pounds. That is the force of the water on this on one side of this vertical plate. Okay, now I'm going to find the work. So this is find the work done by pitching a 6.5 ounce softball at 132 feet per second. In order to find this work, this is called kinetic energy from physics, and the work is given by 1/2 mv squared, where m is the mass of the object right here, and v is the velocity of the object. So we do have to find the mass in slugs though, so the first thing we need to do is to find the mass of this softball by converting 6.5 ounces, 6.5 ounces to 6.5 over 16 pounds, since 1 pound is equals to 16 ounces. All right. Okay, so we have that those 6.5 ounces is equals to 6.5 divided by 16 pounds. But to find the mass from the weight of the ball, we need to express the weight in pounds and divide by 32 feet per second square, which is the acceleration of gravity, since the gravity pulls the ball down. So the mass is equals to 6.5 over 16 times 32, which I'm just gonna leave it like that, and the mass is now in slugs. Therefore, to find the work, we have the work done by pitching this softball at 132 feet per second. It's 1/2 times the mass, which is 6.5, divided by 16 times 32, times the velocity, which is 132 is the velocity squared, like that. Simplifying all of these, you will get that the work is approximately equals to 110.6 foot-pounds. Okay, thank you very much. Next time we're gonna talk about, I don't know, maybe exponential functions and logarithms and the derivatives and the antiderivatives of those. Thank you.